All right. We are very pleased to have Jon Grantham here to tell us about extremely pointless curves.
Thank you. I really want to thank the organizers. This is I think my favorite pandemic era conference, and the only conference I've been to twice now in the pandemic. So that's pretty cool. There are disadvantages and advantages to the online conferences. Usually, I'd be able to tell my non-math friends, "Oh, I'm giving a talk at UGA, USC, Clemson," and they'd be impressed. And if I say, "Oh, well, I'm going to be in my basement giving a talk, and I'm going to have to make sure that nobody's running laundry," that's less impressive. But then I can say, "Oh, yes, and my talk is going to be on YouTube," and that'll at least impress my kids. So that's something. Anyway, today I'm going to talk to you about extremely pointless curves, uh, and this is continuing work with Xander Faber. And at the end of this, I will tell you um, where it's going. I guess what's left to do. So I'm going to be talking about curves and smooth curves, just make your standard assumptions that these are not weird curves. And the gonality gamma of a curve is, it's the minimum degree of a non-constant k-morphism onto the projective line. And if you haven't seen this before, maybe that's a jumble of words, but uh, thinking about the first for small gamma sort of brings it into perspective. Uh, if you have a gonality 1 curve, that just means there's an isomorphism to the projective line. So those are your conics, your genus 0 curves. Gonality 2 curves are hyperelliptic. Hyperelliptic meaning that there's this 2 cover, and so all elliptic curves are gonality 2, but there are also higher genus ones, hyperelliptic curves, obviously. And then for gonality 3, these are what's known as trigonal curves. And as far as I understand, the term gonality is a back formation from trigonal. So what are we looking at? So there's a question, well, there are often questions about, let's say, if you have a given genus over a given finite field, what's the maximal number of points you can have on this curve? And you have various bounds. There's Serre did a lot of bounding on this, and there will be papers. I think I can't remember whether it was mathematics of computation. Everett Howe had one recently saying, okay, here's the field with 8 elements and genus 4, or maybe it was the field with 4 elements and genus 8, or something like that. And here's either a new example or a new bound. And there's a website called manypoints.org you can go to see the sort of current state of the art for the knowledge of these. And van der Geer was in the pre well, not in the pre-internet era, but in the pre-manypoints.org era, was one of the co-authors of an original paper that started this work and indeed turned into manypoints.org. And one of the questions he asks in another paper is, okay, well, what if you put a gonality restriction onto the particular genus and finite field? What can you say about the largest number of points you can have on, as I said, smooth projective curve over a particular finite field? We answered this question for Q is less than or equal to 4 and the genus less than or equal to 5 in previous work. That is on the archive. If you search Grantham Faber, you should get it. You can also go, my math blog is math.pseudoprime.com. And you can see, if you scroll back to late spring, there's a video on there of a talk I gave about it. You can be less impressed because it's on Vimeo rather than YouTube. Anyway, so that work used, in some cases we could just say things about the geometry of the curve that, like, okay, here's an example and here's why you can't have any more points, or we would narrow it down, like a curve would have to look like such and such, and then because of the small size of the field, you're able to exhaust over all possible curves to find the maximum. So that is a different thing for the most part than what I'm talking about today. But let's talk about pointless curves, because that was something we ran across in this search that seemed kind of weird and seemed worth further exploration, which I'm describing here. So you have your curve, and it's a theorem that the gonality is less than or equal to the genus plus 1. And if there's a point on your curve, then it's actually, it can't be bigger. The gonality can't be bigger than the genus. So therefore, a curve with gonality G plus 1 is what Howe, Lauder, and Top called a pointless curve. And so again, a pointless curve doesn't have to have gonality G plus 1, but a curve with gonality G plus 1 does have to be pointless. And what we realized is that for a curve with gonality G plus 1, not only does it have no points over your ground field, but for all r dividing G minus 2, that extension field, it has no points over it. And since it's pointless over all of these ones, we decided to call these extremely pointless curves. And so so when is it possible to have these extremely pointless curves? The Weil bounds are your friend here for narrowing it down. And you can do the algebra and you get this bound on Q that clearly, as G gets bigger and bigger, this bound gets smaller and smaller. Eventually it gets below 2. So there's a finite list of possibilities for the curves. And just from this bound, you can say that genus 3 curves, you have this bound up to Q, Q less than or equal to 32. Genus 4, it's even smaller. Genus 5, there are only 3 possible fields. Genus 6, there are 2, and 7 through 10 is only going to be binary curves that could possibly give you an extremely pointless curve. So again, in the course of filling in this table of the largest number of points for a particular genus and gonality over binary, ternary, and quaternary fields, we had to address a lot of this, but some of this is beyond that scope. So what was known before we started tackling this part of it? So Howe, Lauder, and Top in their paper about pointless curves, basically a genus 3 curve that has the gonality, it's going to be a non-hyperelliptic curve. And so they did what is essentially a classification of that. In our paper on binary curves, we found one of genus 4 over F2. So again, that's going to be a gonality 5 curve. Kastrick and Teutman had already done the genus 4 case over F3. I think they were just mostly concentrated on the odd characteristic case. So we, again, in our second paper where we were looking at ternary and quaternary curves, ruled out a pointless curve of genus 4 over F4. And again, in the course of both papers, we ruled out any for genus 5. So yes, so this says the treatment of binary curves is on the archive. Our treatment of ternary and quaternary curves will be soon. This is slightly out of date. Both of them are there. And again, so far, they're the only papers Xander and I have co-authored, so it should be a pretty easy search on the archive. If you do it quickly, because we're writing another one on a completely different topic. So what does that mean? We have 8 cases left. We have the genus 4 case with primes 5 and 7, genus 6 case with 2 or 3, and then we have the larger cases over binary fields. So what are we looking at here now? After much trying to figure out how to give appropriate credit, we're calling this Lauder's algorithm for Serre's explicit method, because Serre had given these techniques where you compute a list of all possible zeta functions for a particular curve, and then you can look through them and say, okay, these are the possible ones, these aren't possible, and if none of them are possible, then you rule out particular numbers of points. And so what Lauder did, she really systematized it and was able to get a number of results. And so we've taken her technique and applied it to these extremely pointless curves. Again, you have a lot of extension fields over which you have to have 0 points, which is it's a straitjacket on your zeta function. And so that means that it's pretty easy to arrive to a contradiction in a lot of cases. And in particular for the cases I list here, we were able to use Lauder's function to eliminate all possible zeta functions. Okay, so that left, well, it gives us, well, the first theorem is from Howe-Lauder-Top. It classifies extremely pointless curves of genus 3. The genus 4 curves, we were, I guess one would say that was our theorem. And there are only 3 possible other cases that we had to deal with, and it looked like 6-2, 7-2, and 9-2 were not able to be solved, and there turned out to be 2 zeta functions for the genus 6 case, 77 for the genus 9 case. For the genus 6 case, and 1 for the genus 9 case. And then Xander realized that there was a way of representing these curves that was amenable to a search. I can't remember what, there were singular curves of a particular degree that I'm blanking on which one it was right now. But the point is that you can look at those, and you can actually, for genus 6, you can search through them and you can eliminate all of the zeta functions. For genus 7, there's a similar technique, and it would handle, I can't remember, it's either 76 or 77 of the zeta functions. And that would require a much larger computer, which fortunately we have a much larger computer. It would also require some coding on my part. And I have a rule that I will only work on one paper with each co-author at the same time. And Xander sent me a really interesting problem one day. So I told him, okay, now this is on the back burner and we're writing up the other problem. So I think we're going to be able to get all but, let's say, 3 of the genus 7 zeta functions eliminated. And then that last curve, we don't, that last curve for genus 9, I believe that it is something that could be solved with enough computation, but even on a large computer, that came out to years in terms of our estimate for how long that's going to take. So, we're trying to think of ways to speed up the computation, but we may need more clever ideas. And that's why I end this talk saying, I welcome questions, but I also welcome your answers as to how to eliminate the other cases. So thank you.
Let's thank John. Any questions, suggestions, comments?
I have a question. Do the examples of extremely pointless curves tend to be interesting in other ways as well, like super singular or tiny equations?
I'm going to say no. I mean, you can look at, well, so in some sense, right, we only found one because How Louder and Top had found the ones for the genus 3 case, and our genus 2, well, we did find some genus 3 ones that were a little bit simpler, but I think in each of the cases there tends to be not just one, but a bunch of them. And so there are ones with, well, over, it's hard to say what, I don't know. It's, they tend to be a little, we tend to use a little bit of the simpler ones when we were writing up the first couple papers, just because it looked prettier in the PDF. But I don't think I could stare at any of these and tell you, oh, well, clearly something weird is going on with this extremely pointless curve.
Any other questions?
I also have a question. So this is more about kind of what would be next. So have people thought about, the gonality being G, also those curves have special properties like, very few points, or there anything can happen like when the gonality is actually G?
So in our paper, in our second paper, we have a couple of conjectures about what happens. And I think the idea, as I recall, if you get close to G, but not all the way to G, you're going to hit the maximum allowed. But certainly experimentally, when your gonality is G, you have a much greater constraint on everything. And I don't know that we have any examples where you get the maximal number of points, but
yeah, so those tend to have more points than,
well, they certainly don't have 0 points, but
yeah.
if I could, if I had handy the chart from from my previous talks on it, which actually maybe I do. I could put that up to give you an idea of what the sort of experimental results look like. So if I can get that up in the next 2 minutes, you'll see it. Otherwise, go see the paper. So
yeah, I'm definitely happy to look that up because this looks interesting.
So yeah, again, if I can remember, excuse me, when I gave this particular talk. So yeah, okay, that may not, oh, okay, well, let me see if I can. If I can get a couple there. So I'm going to share screen again. I'm not going to be too careful about this being full screen, but I guess for the ternary ones, genus 3, gonality 3, you do is where you reach your maximum, but that's sort of forced by the fact that you can only go up to 8 on the hyperelliptics, and there are curves of more than that. Yeah, so here it's a mixed bag. For 3 and 5 you see it, and for 8 you don't, or sorry, for 4 you don't. And then the binary table here, well, the same thing, honestly, in terms of the genuses. And I think at the time I gave this talk, we did not have the quaternary stuff done, so that would be in the paper. But I'm not sure exactly what to conjecture on where, you know, for each genus and finite field, there's, on many points, you can see what's known about where the maximum is. And once you filter out by gonality, just given there's so many different techniques that get used to prove these results, that I don't know how to say, sort of at the extreme case where you're at the genus, whether that would be maximal or not.
Thanks, John. Maybe you can share these slides on Discord, and we could continue. There's a whole forum for continuing to talk about.
Okay, which channel?
There's a chat about talks.
Okay, I'll upload my slides there.
And like these fun tables, and everyone can look at it, stare at it.
Okay, I will try to do. I'll certainly upload the slides from this talk, and I have a number of other. I actually have some shorter tables for genus for finite fields of size 5 and 7 that I can even upload if I can.
That sounds fun. Like, so the whole conference can then come give suggestions and look for patterns.
Right. Okay.
Thank you.
Thank you all.
All right.